Modeling the Observed Movement of a Slinky by Colin Funkhauser. The purpose of this lab is to investigate the seemingly impossible movement of a falling slinky using GlowScript to create a computational model that will try to recreate tracker data from an observed motion. Through modeling of the slinky and observing the tracker, it can be seen that the bottom of the slinky does not move until the top of the slinky reaches the same point at which they both fall at the same time. The principles are Newton's second law, where the change of momentum is proportional to the net force applied, as well as the drag force, which is resistance due to friction between multiple mediums, and the spring force, where the slinky acts as a spring where tension is equal to the opposite to the gravitational force. So the observed motion tracks the slinky falling, and it tracks the bottom part where the slinky's mass is 0.25 kilograms. The height of the drop is 1.75 meters. The initial position of the bottom of the slinky is 0.599 meters, and its initial velocity is 0 meters per second. The system is the slinky, and the surroundings are Earth and the atmosphere. And the graph shows a 0 change in position until the top reaches the bottom, and then a negative slope in the position over time graph. So computing before the top of the slinky reaches the bottom shows a while loop where the spring force perfectly counteracts the gravitational force during this time interval, and the top of the slinky drops due to gravity, but the bottom of the slinky does not move during this time interval, and the code is shown here. So computational, once the top of the slinky reaches the bottom of the slinky, so there's a while loop during this time interval. The entire slinky drops due to the force of gravity, with drag force counteracting the gravitational force, and the velocity and position update formulas are used to track its movement. So shown in the results, the computational model shows 0 movement until the top reaches the bottom, and then a negative slope until it reaches the bottom, and the model data shows a more erratic graph but similar trend. So some possible errors why these graphs don't line up: inaccuracies in the drag coefficient due to human error, and inaccuracies in tracker, which show a more erratic data set. So why does the slinky fall like it does? The movement of the slinky is due to the spring force of the slinky pointed up, which counteracts the gravitational force pointing down. The tension within the slinky keeps the bottom stationary until the rest of the slinky falls to meet the bottom of the slinky. And then as it falls as if it were a normal mass once the top meets the bottom. Thank you.